Hello friends, so today we are going to solve two more questions, and these questions are from the rotational motion, as well as there is a small concept involved here which we discussed last time also, and that was our center of percussion. So we are going to use the first question. We are given that you hold a top vertex of a solid equilateral triangle plate of side length L with its plane kept vertical. The triangle is stuck by a hammer at some point along its vertical axis of symmetry. Determine the point along this axis where the blow should be applied so that the vertex being held remains momentarily at rest immediately after the impact. And it is also given the moment of inertia of the triangular plate about any axis through its center of mass is ml square upon 24. So in this case, this is basically because it says that the point which is being held should be momentarily at rest. Okay, so this is nothing but a center of percussion is also is related with this concept. And so for this we are given that we have an equilateral triangle whose side length is L. So we can say that we have our equilateral triangle, and we are given that the side length is equal to capital L. Okay, so this is given to us. Therefore, from here we can find out the height of the triangle. Height of the triangle, let us call this as h, and that will be equal to our square root of 3 divided by 2 times L. And we know that our center of mass of the triangle, that is also our standard formula, it will be located at 2/3 of the height h. So we can just draw the approximate figure. So this is an equilateral triangle, and for the height, so this is the height of the triangle, and which is our h, and L is the length of the side, and we can say that its center of mass, let us suppose somewhere here, which is called as G, and that will be equal to our 2/3 of h from the vertex. So from this end you can say it will be equal to, let us call this as D, and then this T will be equal to 2/3 of our total height h, and we can substitute h and we can calculate it in terms of our length also. So we can say that our center of mass, denoted as capital G, is equal to, at a distance d, and it will be equal to 2/3 times h, and we substitute value of h, that is 2/3 times 3/2 and times L. So we can say that our d will be equal to L by square root of 3, and let us call this as A, B and C. So this is with respect to point A. and point A is nothing but holding point. So we are holding from this end, from the point A. Okay, so you can say from the vertex A, okay, and the holding point, the holding point. And obviously from the figure we can see that this is lying on the, this G point is lying on the median. Okay. And so let us assume that the point where we are striking is point P, and it is at a distance of Q from point A. So we can say that the strike point is our P, and it is at a distance of our Q from A. Therefore, we can say that our Q will be lying between 0 and our H. And so we can just assume that the holding point A is having a coordinate of our 0, 0. So this is our origin basically. And so the impulse is basically applied on our point P. Okay, so we can draw only, let us call this as A, B, and this point is our D. So we can draw our median. This is our point A, point D, and H is the height. And we have a G, which is at a distance D. And also we have considered a point P. Anywhere we can consider, let us suppose this is our point P, and this point P is at a distance of Q from our point A. And everything is being measured with respect to point A, because point A is our holding point. We are holding that from point A. And so it means we have to find out this value of Q such that the velocity at A is, for fraction of second, is 0 after the impulse has been applied. Okay, so there is no pivot motion about point A. So from that, we are going to start with linear momentum, and therefore we can say that our linear momentum and we call that impulse which is being applied at point P, suppose is our J. Therefore, we can write that the impulse J imparts linear momentum to the entire triangular body, Therefore, from here we can find out the velocity of our center of mass, that is our G. So we can say our velocity of center of mass, and that center of mass is denoted g, and we can say this velocity of our center of mass, that v of g, will be equal to j upon the mass m. And now we can find out, or we can calculate, we'll try to calculate the linear angular, we are trying to calculate angular momentum about g. Angular momentum about g. And so obviously that will be because of the impulse, or we can say the torque due to j. And you can say that the angular momentum about g, okay, we can say that our angular impulse about g is the torque due to j, is torque due to j. And we can find out the distance between our g to p, which is along to medium. Therefore we can say that our this gp will be equal to our total is our, and we can write this as q minus d, q minus d. And we know that our j is perpendicular to the medium, therefore this q minus d will be acting as a lever arm. You can say that our since j is perpendicular to the median, therefore the lever arm will be our q minus d. Okay, and for the sake of convenience we can just write it as a modulus, okay, because p point we have taken this as a random point. Okay, it can be beyond above g also, or it can be below g also. Okay. So that will be a q minus d, and angular impulse is our j, and the lever arm is our q minus d. Okay. And therefore we can say that the change in angular momentum is our, therefore we can write that our change in angular momentum about g will be equal to the moment of inertia about the center of mass multiplied by the angular velocity, that is our omega. Okay. And therefore we can write that our this ICM times omega will be equal to j q minus d. And from here we can write that our omega is equal to j q minus d upon ICM. And now we come back to our velocity at A, because we are mainly interested in point A. So we can say that our velocity at A And obviously the velocity at A will be the vector sum of our velocity of g plus the rotational velocity that will be relative to our g. Okay. So the velocity of A, this will be our vector sum of velocity of g plus rotational velocity relative to g. And we already know the position of our g from A, that is our distance d. Therefore we can write that the magnitude of velocity at A can say the magnitude of velocity at A, let us call this as our VA, then this VA will be equal to velocity of our center of mass, that is our VG, and that is our omega multiplied by d, because the distance between point A and G is our d. And we want that our point A should not be moving, it should be still for the fraction of second. Therefore we can put here VA is equal to 0. So we substitute VA is equal to 0, and therefore we get that 0 is equal to our V of G minus omega d, which gives us our V of G is equal to omega times d. And our V of G we already know is our J upon M. Therefore from here we can say that our J upon M is equal to, we also know our omega is our J Q minus T ICM times D. And we can just solve for our J, and J cancels out, and therefore we can say our Q minus D will be equal to, this comes as our ICM and divided by M times D, and therefore we can say that our Q is equal to D plus ICM M times D. And we are given the center of mass is already given to us, so there is no need to calculate. Therefore we can substitute it here. So we get Q is equal to D plus 1 upon M times D multiplied by ml square and divided by 24. And here our this mass and mass cancels out, and we also know that our D and the relationship between our D and L we already found out. So we can say that our D is equal to L by square root of 3. So we can just substitute it here, and we get this as our L upon square root of 3 plus 1 upon L square root of 3 multiplied by L square, and this is our 24. And here this square cancel out with L, and this we are left with L upon square root of 3 plus this we have square root of 3 upon 24 times L, and we can just manipulate it, and we can take L as common, so this comes as L, and we can take much better to rationalize, so we get this as square root of 3 upon 3 plus square root of 3 upon 24, much more easier to solve. So we get this as square root of 3 times L, and this will be 1 by 3 plus 1 upon 24. 1 upon 3 plus 1 upon 24, and 3 root L times 24 will be LCM, so this comes as our 8 plus 1, and this comes as our 9. So therefore we can say that our Q is equal to, and we have this as square root of 3 times L multiplied by 9 upon 24, and if required we can just further solve it, we can just rationalize it once again, and that is going to solve our denominator. So this will be coming as 3 root 3 and times L multiplied by 9 upon 24, and this goes by over 8. One second. Yeah. So we get this as L upon 8, and we are left with this as our 9 square root of 3, which can be written as, so we can write this as L upon 8, 9 upon square root of 3. We can further write it as 3 root 3. Okay, once again, if you realize, we are going to get same. Therefore, we get that the value of Q is our 3 root 3 upon 8 times L. So this is our distance of our this point Q from our the vertex. So we here, yeah. So we get this, we were supposed to find out this, so distance Q and this distance Q we found out is equal to 3 square root of 3 upon 8 times L, and this is the condition such that the point A is stationary for fraction of second, because that was a requirement for our in the question given to us. Next question.